Once again, I'm Steve Leytus. I'm from a company called Nuts About Nets, and we're a software company. We develop low-cost diagnostic tools, troubleshooting wireless applications. The focus is the two main applications that we're interested in. First one is Wi-Fi. The other is wireless pro audio. And it turns out that for both types of applications, you can use the same type of diagnostic tools because you're basically trying to solve the same problem. And both of them suffer from RF interference. So in the case of Wi-Fi, usually the goal is to find the channel with the best throughput. And in the case of wireless pro audio, when in a live event, the audio engineer has to assign a channel to all the wireless transmitters, the wireless microphones, and also the in-ear receivers. So in the wireless pro audio field, what a spectrum analyzer helps you do is it helps you create a frequency set that's then used to assign channels or frequencies to all the wireless audio gear. So the topic for this talk is why an RF spectrum analyzer is my friend. And so this is my first WLPC conference. And after being here a couple days, I now understand that probably most of you are very familiar with the spectrum analyzer. So if I were to talk about the value of a spectrum analyzer, I know I would be preaching to the choir. So, but just if you can indulge me for just a few minutes, then I'll tell you why we think a spectrum analyzer is important. So first, I want to just talk a little bit about the distinction between network discovery and spectrum analysis, because network discovery is a tool that most of us use pretty often. And what people use network discovery for is to measure the beacon strength of the APs in our local environment. But just to be clear, you know, the strength of a beacon is no indication of the performance. It's just how close that access point is to the location where you're measuring the beacon strength. And the other thing with network discovery is that it cannot detect RF interference. On the other hand, an RF spectrum analyzer, the lower chart, spectrum analyzer, its goal in life is to measure RF energy. But on the other hand, it cannot see APs. It can't, because it's not doing any sort of decoding. It doesn't see beacons, so it's totally unaware of any APs in the area. And just as an example, in the chart below, we used an RF signal generator to inject some energy around channel 11, and that would totally take out any APs that were using channel 11, but the network discovery tool would be totally unaware of that interference. And here's just another example that a network discovery tool detects beacons from local APs, but it's totally unaware of that cordless phone on channel 1. So Keith, it keeps blinking 104. Oh, that's back, okay. But everybody says an RF spectrum analyzer is expensive. But I can tell you that these days that would be wrong. If you haven't already heard about it, I wanted to mention there's a new product. It's been around for about 3 years. It's called RF Explorer. It's a handheld RF spectrum analyzer. It's very low cost, depending on the model. The cost is about $129 to $365. It can be used standalone. It has a built-in LCD screen. It can also be connected to a PC or an Android device. And so our company, what our niche is that we develop software for this device. And It supports the Wi-Fi bands, both 2.4 and 5 gigahertz. And it also supports other bands, for example, FM, UHF, and cellular. And so I would say that behind MetaGeek's WiSpy product, the RF Explorer is probably now the most popular RF spectrum analyzer on the market. So I just wanted to say a few words about like how when we consult with people, talk with people about how to track down RF interference, there's sort of like 4 scenarios where RF interference can impact a wireless network. And sometimes it's helpful to sort of distinguish between these different scenarios because then it helps you determine the best way to solve it or how you're going to go about solving it. So one type of interference is from non-802.11 devices that will cause an 802.11 device to back off. Another type is when you have adjacent channel interference, where you have 2 802.11 devices, but they're using adjacent channels. That will also cause back off. A third type, which people refer to as CCI, co-channel interference, I prefer to use the word congestion to distinguish that from the types of interference that cause back off. In the case of co-channel interference, the devices will actually arbitrate to share the channel. And so there's this distinction between back off versus arbitrating. And the fourth type is a hidden node problem, and that's when the transmitter is totally unaware of the interferer, and so it will transmit, but at the receiver, the packets are being corrupted. So of these 4 types, probably the worst type is number 4, because when packets are corrupted, it means the transmitter has to resend them. And the last thing that the transmitter wants to do is to retransmit a packet because it consumes CPU time and also resources. So when you detect, so suppose you've now determined that you have a problem with RF interference, what can you do? So one thing is you try to track it down and remove it. Second thing is you try to find a better channel. You configure your access point to a different channel. The third thing is you rely on, it's called DCS, Dynamic Channel Selection. Devin Aiken yesterday was talking about RRM, Radio Resource Management. And that's where you leave it to the AP to figure out what's the best channel to switch to. And I can tell you, like with channel one, with solution number 1, it's really hard to do because for a few reasons. One is that the interferer may not belong to you. Number 2, it might be the wireless security system in the building, and so you can't be taking that down. And the third thing is that even if you wanted to track it down and you had a directional antenna, if you've ever tried to do it because the radio waves are bouncing off of walls, even when you use a directional antenna and you're pointing right at the source, and even when you move a little bit away, the delta in the spectrum analyzer is really small. So it's not like when you're pointing right at it, you see a big peak of interference, and when you point away, it goes way down. The delta is really small. So even if you wanted to track it down, if it wasn't an obvious interferer, it's hard to do for that reason. And number 3 doesn't work so well. I can tell you from personal experience, I spent a fair amount of time at Nintendo testing their wireless Wii U console, and it was a major chip manufacturer. They implemented DCS, and we wasted so much time trying to figure out why it would choose a particular channel, and oftentimes it would pick the wrong one. So in the end, what most people do is they configure their AP to use a better channel. This slide is sort of an exaggeration, but I just want to show you that suppose if you had a spectrum trace like this, how would you choose what was the best channel? Is it I mean, is it worse to have lots of medium strength interference? Or is it worse to have broad low strength interference? Or is it worse to have a narrow high strength interference? And I would challenge, I mean, unless you're intimately familiar with 802.11, there's no way you could figure out what the best channel is here. The only way to test it is to set up an AP with a couple laptops and measure how long it takes to transfer a file from one lab to another, or to use iPerf to actually measure the throughput. So you have to do it empirically. The goal is always to get optimal throughput, because that's what makes users happy. So, so wouldn't it be nice to have a tool that eliminates the guesswork? And that's my segue to my favorite slide. We're coming up with a new product. It's called Wi-Fi Logix. It's a handheld device. It's based on a patent that was published a couple years ago. It uses a dual band 802.11 chip to measure the available throughput of each channel. And since it's the transmitter that drives the throughput, what the tool does, it measures the available throughput. It traverses every channel, and it measures the available throughput on each channel. And in that way, it can rank each of the channels. And a while back, I came across I was reading something that Devin Aiken had written, and he used the expression using 802.11 infrastructure to troubleshoot the infrastructure. And that always stuck with me, and that's sort of the philosophy that drove the development of this device. And it has two main features. Okay, first one is called air horn. Air horn is a signal channel generator. It transmits promiscuously. It's used to test wireless. It's used to test antennas or to stress test a wireless network. And the other feature is called Wi-Fi probe. That's the feature that actually measures the available throughput on each channel and can then rank channels from best to worst. And on that note, this is my summary slide. Thanks for listening.